create the set of equivalence classes associated with this relation R. So this is actually straightforward to do. So what we do is we take every value, okay? We take every value in A, so don't forget A is the set 1, 2, 3, 4, and 5. So we take every value in A. Let's take 1, and let's see what 1 is related to under the relation. So we can actually see that 1 is related to 1, and also 1 is related to 2. So this set contains the values 1, 2. What about 2? Well, you can actually see from the relation that 2 is related to itself. So there we go. And 2 is also related to 1. So we have 2, 1. 2 ain't related to any other value in this particular relation. What about 3? We're nearly there. So what about 3? Well, we can actually see that 3 is related to itself. And, well, that's actually it. 3 is only related to itself. So that set is closed off. What about 4? We can see that the equivalence class of 4 is equal to the set that contains, well, 4 is related to itself and nothing else, so it's just equal to the singleton set that contains one element. And then what about 5? We can actually see the final one, that 5 is only related to itself here. Okay, so 5 is related to itself. Okay, but the important thing here is that these two relations, these two equivalence classes here, are equal to each other. They're equal. There's equality here. Okay. And also, so this is effectively the set of equivalence classes. It's for each element in A, it's the set of values in A that are related to these particular values. You can see 1 is related to itself and 1 is related to 2. So the equivalence class for 1 is 1, 2. 2 is related to itself and 2 is related to 1. So the equivalence class for 2 is also the set that contains 1, 2. So these two things are equal. And what we can hopefully see is that these equivalence classes, 1 is equivalent also to 2. These equivalence classes, which are sets 1, 2, we have 3, square bracket, which is just a set 3. We have 4, which is just a set 4, 4, and we have 5, which is just a set 5. That these are disjoint. Okay, if we take any equivalence class, okay, with and union it or intersect it with any other equivalence class, we actually get the empty set. That's important. And also when we union all of these equivalence classes across them all, okay, all the way across, when we union them, what we actually get is we get the set A itself, yeah? Because when we union this set and this set and this set and this set, we actually get A, okay? We get 1, 2, 3, 4, and 5 when we throw them all into the same set. And also, the intersection of any of these is disjoint. So actually what we now have is a partition on the set A, which is important because we have a theorem that tells us that an equivalence relation forms a partition on a set A. Okay guys, once again this was Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and I hope that this video was intuitive, and more importantly I hope that was helpful for you, and thanks for watching. Okay, bye bye.